Good afternoon, Durgi sir.
Good afternoon, sir.
Exactly at 3 p.m. We'll begin with our session.
Yes, sir. It is exactly 3 now.
Yeah, just we'll start now.
Okay, sure, sir, sure.
Well, good afternoon, all. I welcome you all for today's afternoon session. The speaker of today's session is Dr. B.S. Durgi. Currently, he is working as an associate professor in the Department of Engineering Science and Humanities at KLE Dr. M.S. Sheshgiri College of Engineering and Technology, Belgavi. He has completed his PhD in graph theory in 2014 from Vishweshwarya Technological University, Belgavi. He was a member of Board of Education in the year 2017-18. He has given several number of expert talks to MTech students, VLSI students, and MCA students at VTU. He is having more than 20 years of teaching experience. So this is what the brief introduction of Dr. Durgi sir. Now I am requesting him, please start with his session. Thank you.
Thank you so much, sir. Thanks for your nice presentation, nice introduction of me. Good afternoon, everyone.
Good afternoon, sir.
So today, I'm actually really blessed to be with you all for 1 hour or so. So I'm grateful to SKN Sivagad College of Engineering for giving me this opportunity. As for my presentation is concerned, so I'll be presenting on Fourier analysis. One second. Sir, I'm not able to share my content now here. Hello?
Sir, share your screen.
Yeah, that is what I'm trying. Present now. Yeah. No, okay.
Share window.
Oh, one second. Actually, yeah. Present now.
Yeah, present now. Then you can go for a tab or a window. Don't go for entire screen.
Right.
If your presentation is there, then you can go for a tab. If it is already open.
Yes. Okay. Thank you, sir. Thank you.
Yes, sir. Now your screen is visible. Your slides are visible, sir.
Okay. Thank you.
Make full screen view, sir.
No, I will just put it in slide mode. Yes.
Yes. Okay, sir. It's okay.
Yeah. Thank you, sir. Thank you. So my presentation for next 1 hour or so will be on Fourier analysis. So my plan of presentation is, as this workshop title is Essential Math for Engineers and Researchers. In Fourier analysis, I thought to cover much on Fourier series, because for this Fourier series transform, this Fourier concept, Fourier series is like a fundamental essential. So I will cover, or I will stress upon much on Fourier series, And next, subsequently, I will proceed on to Fourier transforms. So Fourier analysis. So myself, Dr. B.S. Durgi, Associate Professor from the KLE College of Engineering, Belgaum. Yes, Fourier analysis. Fourier analysis is the method of representing any general function in terms of trigonometric series, particularly in terms of sines and cosines. And it is named after this Baron Jean-Baptiste Joseph Fourier, who is popularly known as Joseph Fourier, lived during 1768 to 1830. So contents of my presentation will be background of this Fourier series of transforms, motivational examples, concepts with illustrative examples. So what is Fourier series? Fourier series, as I just told, it is the method of presenting any general functions in terms of trigonometric series. And Fourier was the first person to cleverly note any periodic function can be expressed in terms of sines and cosines. And literally, his contribution is recorded in the history of mathematics. And the purpose of exposition of this theory is to solve the problems posed by the nature itself, mainly how does the temperature on metallic plate distribute over time, and how about given point on the plate. And he introduced the theory for this series for the purpose of solving actually heat equations and vibrations in mechanical branch. Actually, it is the misconception that nowadays we or even our students will think like Fourier series and transforms will be there for only circuit branch students or circuit branch people or any network people. It is not. Actually, this concept is devised to solve the problems in mechanical branch, that too in the problems related to heat transfer and vibration analysis. And he published his two reports, one in 1807 and next one is 1822. 1807, he published his report, which is loosely translated as Treatise on the Propagation of Heat in Solid Bodies. And in 1822, he published his report, Analytical Theory of Heat. And I think after this, or initially, his reports were objected by Lagrange. And later in 1829, his findings were supported by Dirichlet's, subjected to certain conditions. And those conditions are called as Dirichlet's conditions. And then onwards, Dirichlet is associated with these Fourier concept. So Fourier's series is simply a long intermediate function that breaks down a periodic function into simple series of sines and cosines. This we all know actually. So next, Fourier divides these series to solve the problems on heat transfer and mechanical vibrations. And his work is result of arriving at the answers to particular heat equation. So heat equation is actually partial differential equations. So most important application of this Fourier transform is to solve the partial differentiation, even ordinary differentiation, ordinary differential equations also, and integral equations. So some one or two problems I'll touch upon that also later. So as I told, I will stress much upon this Fourier series because I thought like as essential mathematics for engineers would be Fourier series. In this Fourier analysis I'm telling about. And usually these Fourier series, Fourier transforms are perceived by the audience as most difficult subjects. Actually, it is not so. If one is good in integrations, not that higher level integration, just some parts method or something like that, very simple integrations, if one knows very well, then this will not be that difficult. And to overcome this actually, complex Fourier series or exponential Fourier series, to avoid these integrations or complex integrations, exponential Fourier series were introduced. That we'll see in a later section. So Fourier series is an infinite series representation of a periodic function in terms of trigonometric sine and cosine terms. Its typical form is f of x equals to a0 by 2 plus a1 cos x plus a2 cos 2x. So like this, all cosine terms extending up to infinity. Next part is containing b's and sine waves up to infinite number of terms. And the same series we can write in terms of summation expressions in this format. This Fourier series consists mainly, so in so many categories we can categorize them. So first category, it contains constant terms, next cosine waves, next sine waves. And in other way, yes, it contains a0, which we call it as average function value. Next, all AIs and all BIs. A's are associated with cosine wave and B's are associated with sine wave. And this constant A0, electrical people will as a DC component. A1 and B1 are regarded as fundamental frequency. And next, all AIs and BIs for I ranging from 2 to infinity are again the frequency terms, which are the multiples of fundamental frequency determined by AI. So this Fourier series is an expression of the type. It contains average function value, that is a0 by 2. Next, sine functions, and after that, cosine functions. Average function contains a0, which is a constant term. Next, an is the leading coefficients in cosine waves, and bn is the leading coefficients in sine waves in the series. And our goal is to figure out how these coefficients behave at different values in this series. So next question would be here. Can every function be expressed as a Fourier series? So for that, Dirichlet put some conditions. Next, Fourier's theorem is to express any function as a Fourier series. First point, it must be a periodic function. So the function which we are wanting to express as a Fourier series must be periodic function. Next, second condition, it must be finite and defined in some closed interval, not necessarily minus pi to plus pi only. This is the standard interval I've taken just for presentation sake or clarification. And it should have finite number of maxima or minima, if any. Means what? Any function can be expressed as Fourier series if it is not containing any maxima or minima. If maxima and minima are there, they should be finite in number. And next point, if maxima and minima are not there, then what would be the functions? If maxima and minima are not there, then it will be a constant function. And it will be obviously periodic and can be expressed as a Fourier series. Next is, there should be finite number of discontinuities, if any. Here also, the function should not have any discontinuity. It should be continuous. If by chance the function is discontinuity or there are some points of discontinuity, then those points must be finite in number. They cannot be infinite. So this is the next case. Then if Fourier, that function which we are trying to express as a series, Fourier series in terms of trigonometric series, will be possible if it satisfies this condition, and it will be converges to f of x if x is point of continuity. If there are points of discontinuity, if the function is discontinuous, then the value will be average of right hand side limit and left hand side limits. 1 upon 2 times f of x plus h plus f of x minus h. These conditions are called as Dirichlet's conditions. So earlier after I think 1822, Lagrange objected his findings, Fourier's findings. But later, after so many years, some 7 to 8 years, Dirichlet's with the proof, he supported the reports of this Fourier findings. So nowadays they are known or used as Dirichlet's conditions. And if anyone wants to express any function or any signal or any wave in terms of this trigonometric series, first he or she has to check whether it is fulfilling the requirements, means whether it is satisfying this Dirichlet's conditions or not. If it is satisfying, then only one can try, otherwise, yes, it will not be possible. Next, advantages of Fourier series. We all know that any function which is continuous and its derivatives are also continuous can be expressed as Maclaurin's series, which is an infinite series in powers of x. But this is possible only if the function and its derivatives are continuous. Next advantage of this Fourier series is the second point. Fourier series is possible for any type of functions which is continuous or discontinuous. Only thing is it has to satisfy those Dirichlet's conditions. So the Fourier series is useful in expanding the periodic functions because beyond the periodic function, it will be the extension of the periodic nature function. So it is the periodic extension of the function. So here in Fourier series, every now and then we'll have to use the word periodic. Then what is that periodic? That cleared first. Look at the motions of ponies. They will move periodically. You can check their motions, they will be periodic. And in the similar way, forces on the needle, whatever that forces tack, tack, tack it makes, those forces also will be the periodic. Similarly, the punching machines, periodic nature. So it is all just because we know all those that is collected and presented here. How to check mathematically? For more clarification, geometrically, that we'll see next slide. Mathematically, to check any function as a periodic function, whether it is a periodic or not, we'll have to check this. If fx is a given function, in that function, check whether f of x plus L equals to f of x or not, where L is the period. If f of x plus period use the same function, original function, then it will be periodic function with respect to the period that L. For example, okay, next, smallest positive period of fx is the fundamental period or primitive period of the function f. For example, we know that sin x, cos x we are frequently using these functions or waves. They are periodic in nature with the period 2 pi. Because if you check here, f of x, this is function fx. If you replace x plus 2 pi, it is giving again sin x only. By ASTC rule, sin of x plus 2 pi lies in first quadrant, so again it will be sin only. Similarly for cos x, cos of x plus 2 pi is in first quadrant. Similarly for all the next functions also. Hence these functions are periodic functions with period 2 pi. So next here for tan and cot, they are periodic but period is pi here. So there also tan of x plus 2 pi is tan x, because in first quadrant all are positive. But still their period is pi here, because the reason is this: smallest positive period will be the fundamental period. That I'll take in next slide. But the functions like x, x squared, x cubed, cos hyperbolic x, ln x, these are not periodic. For example, if you take, as we are familiar with this straight line passing through origin y equals to x, it is not periodic because y equals to x is a line, straight line, which passes through origin, making an angle with x-axis 45 degree, and its magnitude or length will be of any extent. It can extend up to infinity. So because of that, it is not periodic. It does not repeat. So now, periodic function means it is an event which repeats after every fixed time interval. So that time interval I have here taken as L, it could be capital T. So some example geometrically we'll see. Sawtooth wave. So this is f of x equals to x. There I took fx equals to x, and there I told x is not periodic. But in next slide, that f of x equals to x is periodic. Reason is it is defined here between the range minus pi to plus pi. It is defined in the interval minus pi to plus pi. Means after this interval, it is repeated. That is given here, f of x equals to f of x plus 2 pi. Means after every fixed 2 pi, the event will reoccur, repeat. For example, minus pi to plus pi is a function passing through origin, making an angle 45 degree with x-axis. And after this, next again, this onwards, next up to 3 pi, in the range of 2 pi, again the same function repeating. Similarly here, and it continues on. So this is a periodic function. Same fx is not periodic there, but that same fx is periodic here because of this additional given expression. F of x equals to f of x plus 2 pi is given. Means after every 2 pi, this fx will repeat. That is why this is periodic function with the period 2 pi. So here period is 2 pi. To find the period, you can just take upper limit minus lower limit. Pi minus of minus pi is 2 pi. Next example, minus fx equals to minus k to plus k. It is rectangular wave. So here, fx takes the value minus k between the range minus 2 to 0. Minus 2 to 0, this is the function piece, minus k. It is taking this value. And for the range 0 to 2, it is taking plus k, exactly at the same height or length, it is taking this value. So in one period, the function is this much. Between minus 2 to 2 pieces are appearing. So this is the function, and this function will be repeating for every period of 4 here, because period of this function is 4. How? Because upper limit is 2 and lower limit is minus 2. 2 minus of minus 2 is 4. So like this, many more exist. Next, some properties related to this periodic functions, which are most of the times, particularly for engineers, applied people, these are useful. First result or first property is, if L is the period of the function fx, then n into L is also the period of the function, where n is any integer. So that means mathematically, f of x plus nl equals to fx. In fact, to define the periodic function, we use this equation only for any integer n. Example for this, if f of x equals to cos x, then f of x plus 4 pi equals to f of cos of x plus 4 pi is cos of x plus 2 times 2 pi, cos of x plus 2 pi plus 2 pi, cos of x plus 2 pi equals to cos x and fx we got. So what is this I took? I want to demonstrate this f of x plus nl equals to f of x. And I know that at this point of time, cos x is a periodic function with the period 2 pi. 2 pi is the period of cos x. So L equals to 2 pi here. If I multiply that 2 pi by some integer, then also it will be periodic and its period remains that same. So as 2 pi is the period of cos x, I am multiplied by 2 here, it became 4 pi, f of x plus n pi is equals to fx. So that I express in this way. Lastly, we got cos x plus 2 pi equals to cos x. But the question here is just confusion for some people. Now, whether the period is 4 pi or 2 pi, that will be the confusion for many people, particularly for freshers I am telling. F of x plus 4 pi also equals to fx. F of x plus nl equals to fx. The period of this function now is, it is still 2 pi only. Because least period is the period of that function. For cos x, no, always period is 2 pi only. The thing is, if it is instead of cos x, if it is cos 4x, yes, cos x is periodic function, and cos 4x is not periodic. That is not the case. That I'll take in next result. If fx and gx have period L, and the condition here is both the functions should be having same period. Both are periodic and they have the same common period L, then their linear combinations also will be periodic and their period also will be L only. So 2 or any number of functions you can take which are having some period capital L, you can take their linear combination, they also will be periodic and their period also will be L only. For example, in the same format I have taken, if fx is a cos x plus b sin x, how it will be periodic here, that will check. F of x plus 2 pi is a cos x plus 2 pi plus b sin x plus 2 pi. Then some people will be having the confusion, why did I take 2 pi only here? Why I did not take some other number? Because I know that here condition is fx if I take as a cos x. Cos x is a periodic function with period 2 pi. That is why I should take here it as 2 pi only. F of x plus 2 pi is a cos x plus 2 pi plus b sin x plus 2 pi. And as we know that again by quadrantal rule, cos of 2 pi plus theta is cos x only and sin of 2 pi plus theta is also sin theta only. Because of that, we got back same original function. Hence, we got f of x plus 2 pi as a cos x plus b sin x, which is fx. Hence, it is a periodic. And this I got for x plus 2 pi equals to x. Then period of this function is also 2 pi only. So these were the functions with period 2 pi. Then their linear combination I took. For that resulting function also same 2 pi will be the period. This I feel a bit important. If fx is a periodic function of period L, then f of ax is also periodic function, but period will be L by a. Quite interesting even. For example, we know that sin x is a periodic function with the period 2 pi. Then how about sin 2x? Sin 2x also will be periodic. Its period will be its original period of the function sin divided by this coefficient of x. For sin x period is 2 pi, divided by this a means 2 pi by 2 is pi. So for sin 2x, it is just pi. If it is sin 5x, then it is also periodic. Its period will be 2 pi by 5 here. Whatever coefficient of x will be there, that will be the period for that sin nx. Similarly, cos 3x has period 2 pi by 3 and so on. Then result 4. So here, if there are the functions, number of functions, period of each function will be different. Then, and if I take the linear combination or sum of those periodic functions, the result also will be periodic, but the period will be LCM of all the individual functions period. Result 2 I took there. Sine and cos are periodic functions with period, same period there, L only. Then if I take linear combination, the period will be same number. But here, I'm taking here number of functions, each with a different period, and if I take their sum, then the result will be periodic, but period will be least common multiple of all those individual periods. Fifth one, a constant function is always periodic with any periodic content. Constant function means, for example, very simple example I'll take. If you take a straight line parallel to x-axis, means there y is a function at some distance k. You can take any section of it. Beyond that section, same portion will be repeated. Means what? Same event will be repeated there. So, like that, constant function will be always periodic, and its period will be any positive L. So this is all about the background for this Fourier analysis, and here I have collected some integrals, and for the purpose of taking these integrals or results, these for mathematics people know these look very simple, but for some people these may be useful. Keeping that in mind, I took these results. These are the straightforward results, which, for example, first 3 results will get by orthogonal properties, and next 3 results are with the virtue of integration and trigonometric properties will get these results. Now, coming to this Fourier series expansion of any general function fx. Now, I'll make one point clear. That confusion for particularly, I think, mathematics people, it is there. Fourier series and Fourier transforms, the difference between the two. Fourier series is useful if the function is periodic. Fourier transform is useful if the function is aperiodic. Means Fourier series can be applicable only if the function is a periodic function. If it is not periodic, then Fourier series cannot be used. Then we should have some solution. For that, we'll switch over to Fourier transform. So that I'll take later in Fourier transform section. Just at this point of time, I recall that point or to clarify. Now Fourier series, as we have seen in earlier slides, it is typically this expression, and in this now our aim is to find the coefficients a0, an and bn. Fourier series is all about finding the expressions or values for the constant term a0, the amplitude an and another amplitude bn. So a0, an, bn we need to find, and that will be the only job in Fourier series, nothing else. Other rest all is mathematics point of view I'm telling. Other rest all is just the use of integrations or knowledge of integration. So as here the main aim will be to find, should be to find a0, an, bn. They will be given by these formulae. a0 is 1 by L times a to a plus 2L fx dx. An is 1 by L times a to a plus 2L fx cos and pi by L dx. Pn is 1 by L times a to a plus 2L fx sin and pi by L x dx. So this is the general format for the Fourier series, and these are the general formulae. In the interval a to a plus 2L, But to make this bit simple or easy, this general interval a to a plus 2l, we will divide into mainly two sections. They are, first section or first category is the interval in which pi is involved. Next, second category is the interval in which pi is not involved, which we call as arbitrary interval. It can be any number other than pi. Again, in this pi, we categorize it as two more sections, minus pi to plus pi and 0 to 2 pi. So, our interval is a to a plus 2l. If you take there a as minus pi and l as pi, interval becomes minus pi to plus pi. Series remains same. Formulae will differ here a bit. Type of interval to interval. If the interval is minus pi to plus pi, a naught will be obtained by 1 by pi times minus pi to plus pi fx dx. An is 1 by pi to minus pi to pi fx cos nx dx. Similarly, Bn is 1 by pi times fx sin x sin nx dx. So these are the formulae to find Fourier series in the interval if the interval is minus pi to plus pi. And here, to find the Fourier series for any function, interval must be given. And before proceeding for the solution, we will have to first look at the interval. What type of interval is it? Accordingly, we should take the formula. Of course, in fact, that general formula, whatever we saw in side before that last slide, they can be used, but still more easy to remember. If you divide them in terms of intervals, formula memorizing will be simple, easier. And after all, this Fourier series, Fourier transforms, from mathematics point of view, it is all about evaluating the mathematical parts. Yes, of course, it is formula. When it comes to application point of view, it is analysis part. And that analysis happens after finding after decomposing this given function. Fourier series is all about making the chunks of the given function, dividing the given function, or expressing that function in terms of the components, which are in terms of sine and cosine. Now, represent following curve as a Fourier series in minus pi to plus pi. Yes, some waveform I have taken here, or some curve or some function. We'll have to find the Fourier series for this. To be mathematical, to find that Fourier series, as we are using those integration formulae, we should have the function in equation form. If it is in geometric form or tabular form, it is not possible to use those formulae. If it is to tabular form or even geometric form, if you want to use the same formulae, you have to convert this formats, tabular or this geometric, in terms of equation. Of course, it is possible. Then we'll have to use those formulae to find those Fourier coefficients a0, an, bn. So here, first we shall take the function. This function is, this is the mathematical equation for this geometric shape of the function, geometric form of the function. It has got three faces. So it is a discontinuous function. Minus pi to minus pi by 2, one piece exists, and that piece is, you can check the value of y, it is up to this, and that is 1 here. Y is 1. So it is down the x-axis, below x-axis, it is minus 1. So for this geometric portion of the function, equation is f of x equals to minus 1 in the range minus pi to minus pi by 2. Next, second piece exists between minus pi by 2 to plus pi by 2. And equation of that is, as it is merging with the horizontal line, it is 0. On x-axis, y is 0, that way. and its range is minus pi by 2 to plus pi by 2. And the third portion of the function is this part, and it is existing between plus pi by 2 to pi by 2 to pi, and that function value is again y equals to 1. So this is the function. So these are the transformations from one form to other form. Any function we can express in possibly three types. One is equation format, next one geometric format, and other one is data format. In practical situations, function will be in data format. In most of the situation, it is wave format. If you take any signals, it may be ECG, EEG, anything like that, there you will see the waves or signals. They are geometric formats. But if you work mathematically, then it should be converted in equation format to use those equations. If you are using the software, okay, not a problem. It analyzes there only. But to work manually, geometric or data format must be converted in equation format. So for this equation, now we have to find A0, AN, BN. So if you compute simple calculation, you will get A0 as 0, AN as 0, and BN will be this expression for this. So how to find this? It is simple mathematical calculation. I have not taken directly answer, I have taken for this. So these are the results. And these results I got by using that previous slide, that the formula of A0, AN, BN. And those formulae are called as actually Euler's equations or Euler's formulae. So after finding A0, AN, BN, those Fourier coefficients, we are supposed to substitute them in the typical format of the Fourier series. Then we are getting that as fx equals to 2 by pi times sin x minus sin 2x plus sin 1 by 3 times sin 3x, etc. So this is the Fourier series presentation or harmonic series presentation of the given this function. So it is between the period minus pi to plus pi. In pi there are two types. In non-pi there are two intervals. Next interval is, which is involving pi, is 0 to 2 pi. If the interval is 0 to pi, means function is defined in 0 to 2 pi, then this Fourier series remains same. And those Euler's formula also remain same. Only difference is interval range will differ. 0 to 2 pi will be the range. There it was minus pi to plus pi. Here it is 0 pi. Whatever will be the range of the interval should be taken for the integration. And next it is the evaluation of the integrals. Actually here once, if the formula taken with the values, I mean the limits and function is taken, next process is not Fourier process here, it is integration process. So in 0 to 2 pi, represent this function as a Fourier series. So this is the function here in geometric form, waveform. As we saw in previous case, its mathematical format is required. It is 0 to 2 pi. This is the interval. And in 0 to 2 pi, function is this. It is a straight line passing through origin, making an angle 45 degree with the x-axis. Then its equation is fx equals to x here. In 0 to 2 pi. And beyond this 0 to 2 pi, the same shape will repeat after every fixed interval of 2 pi. So here on computation, again we get A0 as 2 pi, AN as 0, and BN is 2 by pi times minus 1 to n. And here I have taken the solution of this BN. BN is it is actually 1 by pi times 0 to 2 pi x sine nx dx. But one property I have used here, that property is this function is even function in 0 to 2 pi. It is called as even like function, this function, x into sine nx. Because we know that x is odd function, sine x is odd function, odd into odd is even. So I took the property and taken the calculation accordingly. So once if it is taken like this in integral form, next is integration process. X into sine nx we need to evaluate. And integration methods we must be very much familiar with. Of course, for mathematics people, it is not so difficult, but some tricks should be known. For what type of integral, what type of integration method should be taken. Always parts method, okay, need not be taken. Here, if the integrand is product of two functions and one among them is polynomial, then there is a technique called Bernoulli's integration method. It is most useful for the product of two functions wherein one of the part is. You can apply parts method here. For this, no, it is not so difficult. But if this polynomial degree is higher, then parts method takes more number of lines. But this Bernoulli's rule will give the answer in only one line. And how to apply this Bernoulli's rule? Among the product, one of the factor we should take as polynomial, and another one we have to take as integrable. Polynomial as differentiable, other function as integrable. X is differentiable, sin mx is integral. So in Bernoulli's application, writing first term is important. How to write? Write the differentiable term as it is, other term you integrate it. Integration of sine is minus cos, integration of sine nx is minus cos nx divided by n. So writing in Bernoulli's I am telling. Next, this onwards, you have to go on taking differentiation for the polynomial and integration for this integrated part, till you are writing this polynomial part as constant or 0. So second term, as they are alternately plus and minus sign, we should take. So this is minus. Differentiation of x is 1. Differentiation of cos nx divided by n with minus sign is minus of sin nx divided by. This is supposed to be n squared here. Sin nx divided by n squared it should be. But here, then after this, we are supposed to apply the limit. Here also some time saving techniques we need to use, because Fourier series and Fourier transforms consume more time if you are solving the problems mathematically. So if you are applying the limits, check if any term gets 0 for both the limits. Sin n pi, for upper limit, if I take upper limit, sin n pi is 0. So for upper limit it is getting 0, and sin 0 is also 0. So for these two, both the limits, this second term is getting 0, so this should be 0. So you can take that limit for only this part. Then, okay, actually I have here applied the normal way of applying the limits, but you can do like that. Next here, this should be just x cos nx divided by n with 0 to pi. Then take limits only for this. You are writing pi cos n pi divided by n. See, corresponding to this, both the terms are zeros. So if any term becomes 0 for both the limits, then you can just ignore it. I'm getting the result for Bn as 2 by pi minus 1 to the power n into n here, 2 by pi n it should be. Next, time saving is with the implementation of even and odd nature, or by the adoption of even and odd nature. This is not compulsory, but through this also you can save the time in integration. So if the function is even, that integration can be modified. If the function is odd, again integration can be modified. And in this Fourier series, sometimes we will be in a need of only sine series or in terms of only cosine series. In such situations also, this even and odd nature will help us. That we'll see in a later stage. Now, when the function is said to be even, mathematically, if f of minus x equals to f of x, then the function is even. This is for the case only if the interval is minus pi to plus pi or any minus a to plus a form. And these are the results from integration concept. Now, whether this function is even or odd, or when this function will be even. Function will be even if it is symmetric about vertical axis, means symmetric about y-axis. See, now, actually the function will be even if the same portion appears as a mirror in y-axis. So here in y-axis same type is appearing, it is even function. Means that LHS type to the left of y-axis is a mirror image of to the right of this y-axis, it is even function. Similarly for odd function, same I have taken. Now it will not be even, it will be odd. And when this will be odd? Function will be odd if it is symmetric at origin here. So earlier we took here at y-axis, it became even function. If I take its mirror image in origin, then it will be odd function like this. So here, these are the mathematical ways to check even and odd nature. You have to replace x by minus x. After replacing x by minus x, if you are getting original function fx only, it is even. If you get it as minus fx, then it is odd. And now, this is for continuous functions. We will be having discontinuous functions or piecewise continuous functions. In such cases, for checking even and odd nature, in the interval minus a to plus a type is different. For example, if fx is pi x and psi x, it is containing two pieces. Minus pi to 0 is pi x, 0 to pi is psi x. Then, to check even nature, you have to replace x by minus x in first phase. You have to get second phase with positive sign. It is even. If you replace x by minus x and getting second phase with minus sign, then it is odd function. So if the function is piecewise continuous or discontinuous, then we use this for checking its nature. Now, it is for the interval minus pi to plus pi. Now, our interval would be 0 to 2 pi. In this, checking of even and oddness will be different. There we replace x by minus x, but here we should replace x by upper limit minus x, 2 pi minus x. If you get a positive original function, it is even. If you get negative of the original function, then it is. So as in previous case here also, if it is piecewise continuous or discontinuous function, checking for even and odd will be. Replacement is different. Instead of x by minus x, we should replace x by 2 pi minus x. If you are getting positive psi x, it is even. If getting negative psi x, it is odd. Now, these are useful for checking the even and oddness of the product of the functions. If there is an expression with the product of two factors, two functions, if both the functions are even, then it is even. If one function is even and other function is odd, then it is odd. And both the functions are odd, then it is even. And we can very easily remember this by taking plus and minus. To take even function as plus, odd function as minus, plus into plus is even, plus into minus is minus, minus into plus is minus, minus into minus is plus, like that. Then modified formulae. So as just before in one of the problems I told, if the given function is not checked for even and oddness, then we have to use that original formulae, which are with 1 by pi and full interval. If you are getting them as even or odd, then your integral will change. Will change in the sense it is up to our interest. 1 by pi you can take as 2 by pi. If you take 2 by pi, interval become half. It was minus pi to plus pi or 0 to 2 pi. Its half is 0 to pi just. Similarly for an and for bn. Yes, for example, develop the Fourier series for the curve shown in the following figure. So we want the Fourier series for this function. This is in geometrical form. Again, we should write it in equation format. So how to take this? Our period is 2 pi here. It is C 0 to 2 pi. This 0 to 2 pi. This is the function. And beyond this 0 to 2 pi now, function will repeat. The LHS left side I have taken, even the same way it repeats this right side also. And its equation, it is containing two pieces. Okay, it is containing two pieces in minus pi to plus pi I have taken. Yes, in fact, you can take it as 0 to 2 pi also. Yes, minus pi to plus pi I have taken, not a problem. In minus pi to plus pi also, it is periodic. This part corresponds this occurs here, corresponds this here it will be. So between minus pi to plus pi, what is the equation then? It is containing two pieces. First piece is minus pi to 0. In minus pi to 0, functioning taking this value, and it is minus half here. Y value is minus half. So y equals to minus half for this range minus pi to 0. Next, the second piece, y equals to plus half for the range 0 to pi. And once if the equation is written, then for finding its Fourier series, we can use the formula. And here, next important point about this even and odd nature I did not tell. A0 and an. If the function is odd, only we have to find bn, and a0 and an will be 0. Now here function is odd function, because to check the even and odd nature, we know that we have to take first piece as pi x, second piece as psi x. And this pi x is minus of this psi x, no? They are differing by minus sign, hence it is odd function. If it is odd function, you need not find all the three a0, an, bn. You have to find only bn. a0 and an will become 0. And you can check this by that actual calculation. You can go for all the three computation, a0, an as well as bn. You will get a0 as 0, an as 0 there. bn, you may get some answer. In some cases that also may be 0. Some cases I am telling. It is not like that. If function is even, bn only will be 0. It is not like that. a0 and an will not become 0. They may become 0. One of them may become 0. It all depends on the nature of the function. But bn is very sure that it is 0 if the function is even. Here function is odd, a0 and an are 0, bn will exist. And that bn calculation is this, bn equals to its formula fx sin nx. And here I have taken 2 by pi, 0 to pi. In previous one of the previous problems also I took. Here I should take it. There it should be 1 by pi only. But if you check even and odd nature, you can take it as 2 by pi, 0 to pi, and evaluate the integral. And next year, there should not be any confusion. If it is even or odd, is it compulsory to take it as 2 by pi only? No, it is integration rule. You can still proceed with 1 by pi only here. But only the thing is, if you take 1 by pi, then interval should be full interval. Minus pi to plus pi you should take. If you take 2 by pi, interval should be half. So with that, if you take the computation, you are getting the answer as 1 by pi times this. And here this is 2 actually. This is supposed to be 2. So this is the Bn value. And after this, we need to substitute this in the Fourier series 2 by pi sin t plus 1 by 3. We are getting this expression. So here fundamental frequency is 1. These are the multiples of 1, like that. Next, Fourier series of a periodic function defined in a to a plus 2l. So whatever problems up till now, or whatever up till now we discussed, it is for the interval in which pi involvement was there. Now, if pi involvement is not there, if arbitrary interval is there, arbitrary means any number other than pi, then these will be the formulae to calculate a0, an, bn. Here, L value is important. Taking L value correctly is important. After taking L value, we need to substitute and find the series. A periodic motion observed on the oscilloscope is illustrated in the following figure. Yes, this. Find its harmonic series, or represent this in terms of harmonic series. Just write its equation format. This exists between 0 to 0.1. So for this arbitrary interval, you have to read that interval in two ways. One is minus L to L or 0 to 2L. Here, as it is starting from 0, you have to take here 0 to 2L. So 2L is 0.1, then L value is 0.05, this way. Finding L is very important. Now, how to write the equation of this? That is important for such oblique type of functions. So here, I want the equation for this function between 0 to 0.1. These are the periodic extension of the same function. So we want the equation for this. For that, we use from geometry 2-point formula, and we are getting it. So xt equals to 20t, it is the equation of this OA, and xt equals to minus 20t plus 2, it is the equation of this line, straight line a to 0.1. So this is the 2-point formula from geometry. So just for reminding you, I am taking this formula, I am taking its explanation. So for both the components separately we should find. For first component 20t, how we are getting it? This is the fixed formula. This is the equation of the line joining 2 points, x1, y1, x2, y2. Here, I am taking for first this x1 is 0, 0, x1, y1, x2, y2 is this point, it is 0.05 and 1. And if you apply this formula for these 2 points, O and A, equation of OA you are getting, which is 20t. So as we are familiar with x, I took x. So then for my function, I want with respect to time, yes, it is 20t. Similarly, if you take for this other one means for the point A and C you have to take. A coordinates are 0.05, 0.1. C coordinates are 0.1 and 0. Y coordinate is 0. On computation, we get A0 is 0, AN is this, BN is 0. So this is actually the most important part in Fourier series. Mathematical point of view I am telling. Application point of view, yes, applied people in many ways, they will explain it. They'll take oral explanation only for hour or so. But when it comes to mathematical point of view, just yes, it is the decomposition of the function in terms of trigonometric series, and those trigonometric functions are sines and cosines. And next is why Fourier took sine and cosine only. That would be the question here. Can't it be expressed in the form of any rectangular wave or any sawtooth wave or any other wave? Yes, it might be possible. But the purpose of taking this Fourier series or the purpose of devising this Fourier series or Fourier transform is breaking or splitting that given function in terms of the components, because that comes more in transformation section. So anyway, as of now, it is breaking up that given function in terms of the components. So here half range Fourier expansions. This is the concept arises when we are in a need of only sine waves or only cosine waves. Sine waves is always associated with odd function. Cosine waves is associated with even function. So I am finding here for sine series. Sine series is odd function. So it should be, so here function will be given in half range. Instead of minus L to plus L, 0 to L, only half of the interval is given. To find the Fourier series, because fixed interval period is 2L here, so period has to be 2L. So to find Fourier series, this period, this interval must be extended for another half, means minus L to 0. And this extension of this portion of the function depends on our requirement. If you want sine function, yes, it should be extended as an odd function, means we have to take the reflection at origin. So like this, it is reflection at origin, now it is odd. If it is odd function, formula is only Bn we need to find, because as we are in a need of only sine series, A0 and An, whether they will become 0 or do not become 0, you should not look at. If you are taking the extension at origin, they will become 0. But as I am in a need of only sine series, sine wave, hence only Bn we need to find. And Bn will be given by 2L, 0 to L, whatever given interval is there, fx sine n pi by L x dx. Similarly for cosine, if it is required to expand in cosine series, if only cosine waves or signals are required, cosine series is required in the range or interval 0 to L, then same function I have taken, reflection or extension should be taken at mirror image at y-axis this way. In previous, same function I have taken, but I extended the function at origin. But here it should be extended at y-axis or vertical axis. Then we are getting cosine series. And cosine series is associated with A0 and An always. Sine series or sine wave associated with Bn, cosine is associated with A0 and An. And to find A0 and An, same formula, whatever we have discussed earlier. A0 is 2 by L, 0 to L, An is 2 by L, 0 to L. If you take L equals to pi, as I told, interval appears in two formats. One is pi involvement, another one is non-pi involvement. If it is non-pi involvement, whatever previous slide problems formulae are there, if pi involvement is there, you have to just replace L by pi. You are getting the required expression. Now, express this function. Simple function I have taken, and we are familiar with this straight line passing through origin again. Yes, fx equals to x is the equation, y equals to x is the equation. But it is between 0 to 2 only. If this range is not given, then it is aperiodic. That comes in Fourier transform actually. If the period is lengthened or extended or made large for such an extent that t is tending to infinity, then it becomes aperiodic. If it is aperiodic or non-periodic, Fourier series we cannot apply. So here anyway, 0 to 2 is given. So in 0 to 2 only this function is existing. Beyond that 0 to 2, again it repeats. And here we have to extend it in minus L to this means minus 2 to 0. And as here I want sine series, I should take the reflection at origin. So I took reflection here at origin. Now it became odd. If you take reflection at origin, it became odd and it gives us sine wave or sine signal. So now the function is defined in minus L to plus L and its period became 2L. Then we can apply Fourier formulae. And as the sine is required, A0 and AN we should not find. They become identically 0. Only Bn we need to find, and for that Bn, this is the formula that 2 by L. L is 2 here. Next important point, if find only sine series or cosine series, given interval should be compared with 0 to 2L. If the sign is not mentioned, sorry, this sign is not, this sign, SINE, sine series, if this is not there, then this should be compared with 0 to 2L. If it is only sine or only cosine, this should be compared with 0 to L, not 0 to 2L. That is the most time we commit the mistake. By comparing with the 2L, L will take as 1 here. But only sine is there, so L is 2 here. So L is 2 by L, 0 to L, fx sine n pi by L, L is 2, x dx. To compute this, in place of fx, we should take that function is x, and after computation, we are getting this. And substitution gives this as the response. This same function, fx equals to x I have taken in previous case, here also same, fx equals to x, but here it is for cosine. If it is cosine, as we have seen, reflection should be or extension should be at y-axis. So now it became even, it is giving only cosine series. And here also L is 2. Then with that simple evaluation of the integrals, we get the answer as an equals to 4 times minus 1 to the power n by n pi. Yes, this is what all about the Fourier series. If the function is given as a formula, but in practical situation, the Fourier series is also called as harmonic analysis. Fourier analysis is also called as harmonic analysis. Harmonics are that sine, cos, etc. In practical situations, practical harmonic analysis. What is in practical situations? Function will not be given as a formula or the function or the equation. It will be some set of data or tabulated values. So for tabulated values, if tabulated values are given, how to find the Fourier series or how to find harmonic analysis? For that, these are the formulae for Fourier series. This is the Fourier series. To find A0, AN, BN will be the aim here. To find A0, AN, BN, these were the formulae. In previous section we have seen. If statistical data type is given, then how to use these integrations? We have to convert these integrals in the form of statistical formulae. We have to take the average or mean. So if y equals to f of x is the function which is given as a tabulated values, then to convert that integration into statistical formula, this is the formula. Mean value of y equals to fx over the range AB is given by this formula. Between AB, 1 by upper limit minus lower limit of the interval into integration of fx dx a to b. Now, first formula is a0 equals to 1 by pi times 0 to 2 pi. We have to convert this in the form of statistical formula. If you compare with this formula, it is 1 by b minus a means 1 by upper limit minus lower limit. Upper limit is 2 pi minus 0 is 2 pi. So here 2 pi is required, but I don't have. I should multiply and divide by 2 pi, getting this. If I rewrite like this, then it is 2 times this integral, and this integral is, according to this statement, it is mean value of the integrand. Integrand is fx here. So it is 2 times mean value of the function fx in the interval 0 to 2 pi. So if the interval is different, you should take it in different way with the same formula. Similarly, so this is mean value means we know from statistics averaging is summation of all the ordinates divided by number of ordinates. So summation of y divided by n gives in statistical form, in numerical form. Similarly, if you take, if you convert the formula of an and bn, you will get this, because integrand there will be y cos nx divided by number of ordinates. For bn, formula is integrand y sin nx divided by n. And here n is the number of ordinates, means in the table, whatever number of values are given, those. So again, this Fourier series, here, if statistical data is given, then whatever is asked or whatever is our need, only that much we can find, not the general function. If you want only fundamental harmonics which are containing only fundamental frequency and amplitudes are a1 cos sx plus b1 sin x. So if only that much is asked, your computation will be simple. If next harmonics are asked, a2 cos 2x, b2 sin 2x also, then more work is involved. Similarly, a3 cos 3x, b3 sin 3x, still more is involved. So it all depends on our requirement, and the same we can express in this way. So constant term a0 by 2, first harmonic, second harmonic, these all will continue in the same way according as the frequency number you can take. 3x, third harmonic, nx, nth harmonic. So one simple example, the turning crankshaft of a steam engine of the crank angle theta is as follows. So this is one lab data of the mechanical department. They obtained this data and they are in a need of Fourier series expansion for this. They need to analyze this, they want to analyze this, and how to find. For that we use that previous slide expressions. So it is up to first harmonic mentioned, so only up to first harmonic we should take. Next all just we can ignore. Then to find this series, we need to construct a table. That table is this. First two columns should be dedicated to the given data. First column we can dedicate for independent variable. Second column we can dedicate or devote for variable. And next subsequent column should be for the required expressions. I want cos 1 theta and sin 1 theta, cos theta, sin theta, 2 columns. Now I want here actually t cos theta and t sin theta, 2 more columns. If you want up to second harmonic, then you have to take 4 more columns. Cos 2 theta, sin 2 theta, t cos 2 theta, t sin 2 theta, that way. And after that you have to find the column sum for all these t cos theta, t sin theta. Because the formulae are, see, t by n, summation of t by n, summation of t cos, summation of t sin. So we want summation of t cos, summation of t sin. We have got them as these values minus 20.4992, 8.92. Substitute them to get this answer. So here that t will be 4.95. This is constant value. Minus 3.4165 amplitude. Cos theta for first harmonic. Fundamental frequency 1.4839. So this is about the harmonic analysis. So with this now, the basic Fourier series completes. So this is all about the Fourier series knowledge. If the function is given in terms of tabulated value, or if the function is given in terms of geometrical format, if the function is given in terms of equation format, we can use that all to find the Fourier series. Now, next form of Fourier type of Fourier series is exponential Fourier series. Exponential Fourier series is this fx equals to. So here with this fx we are expressing in terms of exponential Fourier series, which is also called as complex Fourier series. This is supposed to be complex. Then why this Fourier series? Already we know that. There what you know, sometimes what happens, finding a0, a and bn as they involve integrations, sometimes that integration may be a bit unpleasant, not comfortable. In such cases, we can prefer to go for this complex Fourier series. In complex Fourier series, it is the summation of the expression. Of course, integration is involved here. So we need to find here just Cn, but that Cn involves the integration. But compared to previous integration, here the integration becomes very simple because it involves the exponential. And we know that integration of exponential involvement will be a bit comfortable compared to other integrals. So if sometimes we can prefer to go for exponential Fourier series. Next, Fourier transform. I'll complete in another 10 minutes. So Fourier transform means, we know that transformation means it is change, general meaning, changing or converting. Fourier transform means it is an operator which converts one form to other form. So here it converts time domain to frequency domain. So in time domain, waves or signals will be complex in nature. They are required to be analyzed. For example, any EEG or ACG signals you can take, they will be complex in time domain, but they are required to be analyzed. Analysis of that signal will be very much complicated. So it can be decomposed or broken into pieces or components. For that breaking, we can use this frequency domain, and for that tool is this Fourier transform. So this Fourier transform is actually, it is continuation or extension of Fourier series, or we can still further we can refer it as generalization of Fourier series. Fourier series is restricted to periodic functions, but Fourier transform we can use for aperiodic function also. And as I told previous instantly, if the period is made larger and larger, and if it made to tend to infinity, then it will not remain as periodic function. It will be aperiodic. For example, that function one of the geometric shape y equals to x I explained there. It was defined in the range -2 to +2. Restriction was there, means beyond that interval -2 to +2, it is repetition of the same event x, y equals to x. So there it was periodic. But if that interval -2 to +2, it is 4. 4 is the period there. If that period 4 is made larger and larger for such an extent tending to infinity, then it becomes aperiodic. If that is the case, Fourier series will not help. Then we have to switch over to Fourier transforms. So here this Fourier transform is, it breaks the main function into in terms of its components. For example, one simple I found, I took it. Musical chord, if its analysis required to be done, then take its mathematical format, then it can be decomposed into, its components are volumes and notes. That musical chord can be divided or broken in terms of volumes and notes, then it can be analyzed, then the consolation. So these volumes and notes will exist in frequency domain. So in time domain it is musical chord, in frequency domain we'll get its components, volume and their constituent nodes. So these are the formulae for Fourier transform. Fourier transform formula we'll get from integral equation, Fourier integral. This is that Fourier integral which we can rewrite in the form fx equals to 1 by 2 pi times minus infinity to plus infinity e to the power minus I sx into e to the power ft into st. So here s is lambda. Then this fx is product of two integrals. Then these two integrals are or will act as Fourier transform and inverse Fourier transform. So Fourier transform, anyone you can take. There is no restriction. So you can take this as Fourier transform or this as Fourier transform. Just the difference is here I is supposed to be taken. Minus sign will be the difference. Here minus Isx, here plus Isx, that way. So then this 1 by 2 pi shall be taken for either to this fs or fx. Fs means this is the formula for Fourier transform. This is the expression for inverse Fourier transform. This 1 by 2 pi can be taken for inverse or for this Fourier transform, direct transformation. Or still this can be made symmetrical factors and can be taken for both. For example, root of 1 by 2 pi and root of 1 by 2 pi. Because this 1 by 2 pi I can express as root of 1 by 2 pi into root of 1 by 2 pi. So that 1 factor can be taken for both the integrals. And here Fourier transform will convert the function in time domain t to frequency domain s or omega or lambda. So Fourier transform converts time domain to frequency domain, and this inverse Fourier transform converts the function from frequency domain to time domain. This is supposed to be t. So those were the formulae for general Fourier transform. Then we will be in a need of only sine or cosine transforms. So these are the formulae, and every transformation is associated with their inverse transforms also. So as we have seen there, even and odd functions, similarly these are the formulae here. Integration range here is infinite. Since there it is a periodic, so interval was finite, but here it is infinite. So I have not taken any mathematical problems here. Just to show one I have taken, just like a computation point of view. Find the Fourier transform of ft equals to 1, 0. So we are required to draw this as a geometrical shape. Of course, not required for mathematical purpose. Just I have drawn. F of t equals to 1. Function is taking the value as 1. Between t is less, modulus of t is less than 1. And it is 0 for all the moduli value of t greater than 1. To find the Fourier transform of this, we have to use this data in integration. For integration, we want the actual range or interval. Modulus of t means it is lying between -1 and +1 in this way. Next, this modulus means, because modulus sign ignores the negative sign, modulus of +1 and -1 will be same. So it is inclusive here. Less than is inclusive. So inclusive from minus sign to plus sign of the same number we should take. This function exists. And greater than means it is exclusive. So less than -1 and greater than this +1, the function is 0. And if you take for Fourier transform, this is the formula -infinity to +infinity, f of t e to the power ist dt. But here function exists between only -1 to +1. Rest of the part it is 0. 0 in the sense what? There also that signal is there, but it is merged with this horizontal line. So here integral range will become -1 to +1. Function in that range is 1 e to the power ist. Simple computation gives 2 sin s divided by s. Now, Fourier transforms are most importantly used in solving partial differential equations and integral equations. So how to use this to solve partial differential equation? Okay, one equation I have taken, dou u by dou t equals to k into dou square u by dou x square, with the boundary conditions t greater than 0 and x lies between minus infinity and plus infinity. Further conditions, u and dou u by dou x tending to 0 as x tends to plus or minus infinity, and u of x0 equals to fx. So this is the partial differential equation with boundary conditions, boundary value problem. We have to solve this. How we can use Fourier transform for this? We have to apply Fourier transform. There is a section Fourier transform of derivatives that we have to apply here. You take Fourier transform for each of the components. You'll get here for dou u by dou t Fourier transform by dt of u bar lambda t. Fourier transform for second derivative is minus of lambda square into u bar of lambda t. And substitute these two in different equation. You are getting some differential equation. It is simple differential equation which is ordinary differential equation. And here variable separable is applicable. If you solve the differential equation, you are getting log of u bar equals to minus k into lambda square t plus c. And u bar is t equals to a into e to power minus k lambda square t. So by applying transform, we got this expression, u bar of lambda t. But we want u of solution of any function means, particularly any derivative means finding the value or expression for dependent variable. And that dependent variable is the function of two independent parameters x and t. So we have to find u of x comma t. But here we have got u bar. So as I want u of xt, we have to apply inverse Fourier transform. If you apply inverse Fourier transform, you are getting f lambda as this. And by using those initial conditions, boundary conditions, we'll get the value of capital A as fz. And after substituting fz, again of course, we'll get integration. Then we have to use mathematics, integration knowledge of mathematics, then we'll get u of xt. But that the partial differential equation we could convert in the form of integration, then these will be simple integrals we'll have to evaluate to get the required answer. And lastly, to solve integral equations also we use. So here also in the same way, to solve integral equation means this is the integral equation. For solving this equation, what is required to be find or obtained, that will be the confusion most of the times. It is integral equation and the variable of the integral equation is x and the function is fx. So we need to find fx value here. And in the Fourier transforms, we mechanically use small f means inverse Fourier transform, capital F means direct Fourier transform. So here we need to find small fx. So inverse Fourier transform formula we need to apply. If you apply that, this RHS given is, because you can compare this, fx cos alpha x dx between 0 and infinity means this is Fourier cosine transform. So since this is Fourier cosine transform, fc of alpha value is e to power minus alpha x. So e to power minus a alpha into cos alpha x dx. Then if you evaluate this is supposed to be x, you are getting this as 2a divided by pi into a square plus x square. So this is the answer for this. So these are the two applications I took for solving partial differential equations and integral equations. Thank you very much.
Okay, sir.
From a mathematical point of view, and some of the applications in the sense what the terminology applied people will use, just that I have taken.
Okay, sir.
So
There
I
is
want
one
to
question.
clarify from my just a minute, sir, please.
Yes,
So
yes.
here, as here, it is the title of the workshop is essential mathematics for engineers. So I thought first to take some application point of view, some research papers I wanted to cover here. But as it is essential mathematics, I thought to cover Fourier series in detail, so that applied people can just recall their BE times to remember the formulae. And after all is here to remember the formula and apply mathematical point of view. Once if you get that mathematical equation, then as applied people, you can very comfortably convert to your applied format, physical format. Yes, thank you again, one and all. Yes, sir, please.
Sir, there is one question from the participant.
Yes, sir.
How can we determine the period of every complex function?
Every complex function?
Yes,
No,
that was the question.
Okay. No, sir, here function will not be complex. See, to find the Fourier series period is required. For Fourier transform period is not required. So to find Fourier series, if you are deciding to apply Fourier series, you see it is understood that you know the period because that function is defined in period only, no? So that only, there is nothing to find that the Fourier period there. Function will be defined in some time period, something like that. If you are applying Fourier series, yes, period will be there. That function is existing in that particular period only. Yes, that only you should take there as a period.
Well, one more question from one participant.
Yes, sir.
Question is, what is the advantages of Fourier series?
Yes, that is what, sir. Advantages of Fourier series means we have one infinite, Fourier series is infinite expression. It is a series of infinite number of terms. Any function we can express as sum of infinite number of terms by applying Maclaurin's expansion, also Maclaurin's theorem. But in comparison with that, Fourier series is advantageous in the way this can be applied for discontinuous functions as well as continuous functions. So that is the advantage here. And it can be applied for the function in particular period. Beyond the period, we are not considering the function here. That function we are considering only in that period with the knowledge that that same function is extended beyond the period, same event is repeated there. It is the periodic extension. So that is the only advantage here. And,
okay, sir.
Okay, yes. Yes, sir.
Okay, now I am going to conclude the session.
Thank you, sir.
On the behalf of SK and Sinhagad College of Engineering, Pandharpur, I have expressed my sincere thanks to Dr. Durgi for his very nice presentation on Fourier series and Fourier transform. Thank you, sir, once again.
Thank you, sir.
And with this, I am concluding today's session, afternoon session.
Thank you,
Thank
sir.
you all.